My name is David Ibbott, composer and director of Multiverse Concert Series, a non-profit that combines music and science in live performance. Today, I'm thrilled to present Multiverse Other Skies, the musical component of Other Skies, an exoplanetary festival in collaboration with CLOT Magazine and SciArt Initiative. In this show, we're proud to be featuring our guest scientist, Dr. Clara Souza Silva of Harvard, back for her third appearance with Multiverse. We'll also have guest musician and scientist Matt Russo and System Sounds, together with pieces from my own album, Octave of Light, an album of exoplanet music performed by myself, violinist Amelia C., and soprano Beth Sterling. Without further ado, I'd like to pass you over to Beth.
Hello, everyone. I'm very excited to be performing this piece for you today. As David said, this is a piece from our album called Octave of Light, which was premiered in November of 2020. We've been working on it together for almost 2 years now. We finally got to premiere it after working on it through quarantine in November. And this particular piece that I'm going to be singing for you today, Wanderers, we actually premiered it for the first time about 2 years ago. So I'm very lucky I get to be performing it again virtually for you this afternoon. Darkness, immortal. Darkness, darkness, immortal. There is a wide, yawning, black infinity. The extension is endless. It is pure, fierce, and blazing, but light exists almost nowhere, and the darkness itself is just as pure, pure and fierce and blazing, blazing, We began as wanderers. 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 We are wanderers still. We have lingered too long on the banks of the cosmic ocean. Darkness, 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 immortal. Darkness, darkness, immortal. Even these stars, which seem so numerous, are as sand, dust, or less than dust. In the enormity of space, in which there is nothing, nothing, the great silent space between worlds of light and darkness pure, light and darkness blazing. began as wanderers. We began as wanderers. We began as wanderers. We began as wanderers. We are wanderers still. We have lingered too long on the banks of the cosmic ocean. We began as wanderers. We are wanderers still. We have lingered too long on the banks of the cosmic ocean. We are ready to set sail. We are ready to set sail.
Let's have a huge round of applause for Beth. I promise you, she can hear you. Thank you so much, Beth. Gosh, I wrote that about 2 years ago, but I really feel like today is the day that it was written for. When I started on this Octave of Light project, it was just an idea and a single friendship with Roy Gould, a scientist who inspired me, and I'm happy to say it's blossomed into a community of artists and scientists who are all passionate about space and exoplanets and connecting with each other. So that was Wanderers, and the lyrics were adapted from Carl Sagan, a beloved scientist and science ambassador who inspired so many of us to do what we do. It's now my great pleasure to introduce another inspirational science ambassador, and I'm proud to call a friend. Clara Souza Silva is a quantum astrochemist at the Harvard-Smithsonian Center for Astrophysics. She investigates how molecules interact with light so they can be detected on faraway worlds. Clara spends most of her time studying molecules that life can produce so that one day she can detect an alien biosphere. Her favorite molecular biosignature is phosphine, a terrifying gas associated with mostly unpleasant life. When she's not deciphering exoplanet atmospheres, Clara works hard to persuade the next generation of scientists and now artists to become an active part of the astronomical community. Over to Clara. Hello.
Hi there. Thank you for the lovely introduction, David. I will share my screen. Carl Sagan, in his 1994 book, Pale Blue Dot, said that we invest far off places with a certain romance. The appeal, I suspect, has been meticulously crafted by natural selection as an essential element in our survival. And that is true for me. And indeed, I do spend most of my working hours investigating possible far-off places all over the galaxy. But I often wonder, if there is life out there, do they feel the same as I do? Imagine there was an alien astronomer on the other side of the galaxy looking for a habitable planet in her night sky. From their perspective, we would be about 2/3 in where you see on the screen. And if that alien astronomer pointed their powerful spectroscopes at our sun, they would be able to split its sunlight into the sun spectrum, and this is exactly what they would see. They would see that some of the light from the sun would have been absorbed by atoms and even molecules in the cooler regions of the sun where molecules can survive, and leave behind these tiny shadows or absorption lines. And that is because molecules behave in a very unique way. Molecules have to follow the laws of physics, but not the same physics as we are used to. Molecules are so small that their physics follows the rules of the quantum world. And one of those rules is that they absorb quantized amounts of energy, and these correspond to specific wavelengths of the light spectrum, and consequently they leave unique absorption lines on a stellar spectrum. Different stars have different compositions and consequently a different spectrum, and this is our sun's unique spectral fingerprint. So that alien civilization could look at this spectrum And using their universal knowledge of molecules that they got from their quantum astrochemists, they would be able to know exactly which molecules and atoms were causing these absorption lines and figure out the composition of the sun. But if they were patient and fortuitously aligned, they would notice that every 12 years, a few additional absorption lines would appear and then disappear and then appear again 12 years later. And these lines we due to the molecules in the atmosphere of Jupiter as it crosses in front of the sun, and molecules within itself also absorb new absorption lines. So that alien civilization with only slightly better technology than we have now would be able to study these lines and know that Jupiter has a huge atmosphere with not just hydrogen and helium, but also methane and ammonia and hydrogen sulfide and many more gases. And if they were really careful, every year, a few much fainter shadows would appear and then disappear due to the molecules in our Earth's atmosphere also absorbing new lines of the sun spectrum. And that alien civilization could study those absorptions and know that we are a thriving, complex, living planet. You can think of our atmosphere and its subsequent spectrum as a planet-sized message, communicating to the galaxy that we have oceans and forests and varied ecosystems with rich life cycles, and also that we pollute an awful lot. These alien astrophysicists could do this for all of the solar system planets and tell the difference between them by looking at the atmospheric spectrum of each planet, which can be represented by these lines you see on the screen instead of rainbows, which are pretty but really hard to analyze. Now, if they did this, they would learn that Venus is mostly hell with very high levels of sulfuric acid, so any life there must struggle, though more about that later. And they would learn that Mars has a teensy tiny atmosphere that can barely shield its surface from radiation, so also not the most hospitable destination. And they would notice that out of the solar system planets, there's something really special about the Earth, and that is we have a lot of life. And with our current knowledge and technical abilities, we are at the brink of being able to do the same to them. But how do we know what to look for? We could, for example, look for molecules that we know life produces called biosignatures. These are molecules that life that we find pleasant loves to make and release into the atmosphere, such as methane and carbon dioxide, which are produced in large quantities by life. But also we can look for molecules like hydrogen cyanide, which, although aren't particularly popular biosignatures now, it was likely crucial as a building block of life, so it's a good pre-biosignature. We know of these gases and we can and should look for them on exoplanet atmospheres, but none of these molecules on their own would necessarily indicate life, as they all have false positives, which means they can be produced by life or by non-biological processes such as volcanism and lightning. You can see on the screen, the first column are ways of life producing these molecules, and the second column are ways of the same molecules being produced without the intervention from life. So this is called a false positive problem. And it happens because these molecules are great, but thermodynamically speaking, they're easy to make. And so life makes them, but they also form accidentally without any life being around. Which means if we detected any of these molecules in isolation on an exoplanet atmosphere, that wouldn't necessarily indicate life. And the main solution to this false positive problem is to carefully consider context. For example, oxygen on its own may not be a good biosignature, but in the exact context of our planet, our sun, and the other components of our atmosphere, oxygen is a wonderful biosignature. And the same is true for most biosignatures usually considered in the search for life in the galaxy. These molecules are only good biosignatures if they can be attributed to life after an investigation of their false positive scenarios, which requires not just an understanding of the stellar and planetary environment, but crucially, the detection of other, potentially much less abundant molecules that can provide context to a discovery of a potential biosignature. But to detect any of these molecules, we need to know their spectral fingerprint, which isn't a trivial thing to obtain. Each molecule has their own spectrum, which look roughly like this that you see here on the screen, describing how it interacts with light. These spectra represent the frequency and the intensity of the quantum vibrations and rotations of each molecule. And each of these spectral fingerprints take years of work to figure out, and we as a species have only been able to fully obtain them for a handful of molecules. Completing this work is the primary goal of my research. Because it's fascinating to me that sometime in the very near future, questions as ambitious as, does that planet host life, will likely be answered by understanding something as small and fundamental as the quantum behavior of molecules. But this behavior is not simple, and despite it being the focus of my work, I often find myself struggling to understand it, wishing I had better tools to visualize and comprehend what the spectroscopy of planet atmospheres, molecules, and life will look like. So, on that note, I would like to direct your attention back to David, who will talk about his work transforming these quantum vibrations of spectra into something we can all hear.
Thank you, Clara. If, like me, you're inspired by the work of scientists like Carl Sagan and Clara, you'll understand why, as a composer, I was inspired to write Octave of Light, this album of exoplanet music. As I said before, the project began about 2 years ago now, through a friendship that I struck with Roy Gould of the Harvard Smithsonian Center for Astrophysics. Roy introduced me to the field of exoplanet science and spectroscopy. And I was stunned to learn that just in my own short lifetime, over 4,000 exoplanets have been discovered through a variety of techniques. As we've learned, these planets appear to us as just a dot, a single pixel representing an entire world over a period sometimes spread out over years. Pale blue dots, all different colors. It still astounds me to learn still that this dot is enough for us to learn about that planet. Clara talked about each planet having a unique spectrum, combination of colors spread throughout the electromagnetic spectrum. These have fascinated me too. So I'm going to put one up for you. What do you think? This is one of the first things that Roy Gould showed me. This is planet WASP 17b, wide-angle survey of planets, second from the sun, that's the B, from its sun, I should say. I mean, the graph looks interesting. There's obviously some, there's that big dip and then some peaks. But if you look at the bottom there, you'll see that colorful part on the axis there, or actually at the top as well. That's where visible light falls. So that's what our eyes can see. And you'll notice that sadly, most of the data here, and this is not even the complete electromagnetic spectrum, most of it we can't see. It's beyond the scope of our eyes. I began to wonder, well, okay, if we can't see these planets, maybe we can hear them. The eye can detect about one doubling of the frequency, which fits in all of our colors we can see. We can call that one octave of light. In comparison, our ears have a much, much wider range, about 10 octaves for the best human ears. That's some of my students. So that's even more than that, actually, a bit higher than that, a bit lower. It's my old English piano, by the way. She's been traveling with me for many years. So I got to work and I thought, well, okay, perhaps we can perceive more of what is there if we translate these light frequencies into sound. We call this sonification. And it works here because light and sound are both waves. They're both oscillations moving through a medium. The only trick, light frequencies are a lot faster. So we have to bring it down about 40 octaves. But the notes are still precise. So when I play a G here in a second, it is a G, just 140 octaves up from what you hear. And to play them on the piano, I have to round the frequencies to the nearest half step. So the one I began with, the first spectrum, is water vapor, which obviously that's, as far as we know, that is very important for life. Just going to put that on my screen here. So here's another graph. It looks interesting. There's obviously some features there, but oh dear, almost all of that is outside of the visible range. So here we go. If we run that through some translation, we can convert these dips, which are the absorption lines, where the water vapor in the atmosphere of a planet absorbs water. This is a model in a lab, but you'll see in a second. We found this on exoplanets. And This is what comes out. And there's a wider version that I sometimes use. And in fact, you've already heard that. That spectrum is in the Wanderers track that you heard. And it's also part of the very first piece I wrote called Water Romanza. And I'll just play you a little bit of that. So going from a chord, come right into a piece of music. Many pieces of music are built directly on top of a chord, and I had a lot of fun projecting my own enthusiasm and thoughts about water on other planets into that piece. So I said that you'd heard it before in Wanderers. In fact, Wanderers is based around the spectrum of an entire planet. Here it is again. So this was 17b again, and here is that spectrum converted into light, into sound, and you might recognize the chord. Any jazz musicians in the audience might recognize that one as an augmented ninth. It's certainly got a twang to it, but the fun thing is that we can break it apart, and you'll see within there we have some of the notes or the frequencies of the water vapor spectrum, and sodium and potassium can be linked to certain notes. So over the course of the project, I've been able to pick out musical harmonies that match up to these frequencies, that tell us things about real planets that have been discovered, and we're learning more about them. So I'm going to pass back to Clara to talk about another spectral feature of interest.
Thank you, David. If you were lucky enough to see Tiana's presentation early on peering through planetary dusk to try to look at alien planets, and if you heard what I talked about earlier on detecting molecular signs of life through their spectrum, you will by now know that there are many ways of attempting to see the almost imperceptible signs of life on a distant planet. And an interesting thought is, if an alien civilization had more powerful telescopes than we do and could actually image the Earth, even at very low resolution, would they be able to see life? Well, at night, they might see the very faint sign of city lights. But what if they were looking about 1,000 years ago, before we had any electricity? Well, if they had really impressive telescopes, they might be able to see an extremely promising sign of life on Earth, and that is from the extraordinary spectral signature of plant life. Chlorophyll is a strong absorber in the reddest portion of the optical spectrum, causing this red dip you see on the screen. But then the cell structure of the plants aggressively reflects the light in the near infrared, that's the NIR bit you see here, causing this distinctive spectral uptick you see here. And this is what the red edge looks like. But now I will introduce you to a red edge musical piece with the inimitable Beth Sterling.
deciduous plants give off light in distinctive patterns. The human eye sees green, but the infrared is stronger. The chemistry of life we know is the same in space. So extraterrestrial vegetation may show similar spectra. Although I'll never be there to breathe the air, I promise you we'll see them. Join me at the red hedge, where we start to grow together. Come follow past the red of the spectrum visible to colors bright like snow. Join me at the red hedge. Join me at the red
We just heard the red edge, which is a sign of plant life we cannot yet see on an exoplanet. And we talked about the many biosignatures we can look for on a planet and how most of them will need a lot of context to be able to be associated with life because they have false positives, meaning that if they are detected on an exoplanet atmosphere, maybe it means life or maybe it doesn't. But there are a few molecules that are really, really hard to make, and so have very few false positives for life. And my favorite of these biosignatures is phosphine. This is what the molecule looks like, phosphine, with a phosphorus atom on top and 3 hydrogens at the bottom. And when we look for this molecule in space, this is what we look for. Here is the molecular fingerprint of phosphine, composed of a collection of 16.8 billion spectral features. I spent the majority of my 20s computing a complete quantum chemical simulation of the phosphine molecule, which means we now know what it looks like and we can now spot it on distant worlds. But why would we want to? Well, phosphine is a very special molecule. It's a marker for violent storms on Jupiter and Saturn. On these planets, phosphine is detected in the observable layers of Jupiter and Saturn, but we really shouldn't expect to find it there because phosphine is extremely difficult to make. Phosphine needs much higher temperatures and really high hydrogen pressures to be made spontaneously. But what happens is that phosphine is a scrappy and resourceful molecule. So after being happily formed in the hellish depths of these planets, it resiliently makes its way to the top, surviving in large concentrations before ultimately being destroyed by its atmospheric neighbors and the sun's radiation. But on planets like the Earth, phosphine is never made accidentally. On Earth, phosphine is mostly known for being a horrific molecule. It is a really effective killer, which is why it is widely used as a pesticide and why it was used as a chemical warfare agent in the First World War and sadly most recently by ISIS. So humans make it, but not just humans. Phosphine is extremely toxic, deadly so, but only for life that uses oxygen metabolism like we do, and most life on Earth. However, there are a few biological niches on Earth that are populated by anaerobic life that is not reliant on oxygen. And on Earth, these environments exist, though they are poorly studied, and here phosphine is not so evil. I'm talking about places such as sewage or marshlands or rice fields, lake sediments, the intestinal tract of fish, the intestinal tract of babies, and actually the feces of penguins, farts of badgers, and the intestines and excrements of most animals. All of these are complex, rich ecosystems, and what they have in common is that they host anoxic life, life that doesn't need oxygen, and they produce phosphine quite happily, since it is only phosphine's relationship with oxygen metabolism that makes it so deadly. But for the majority of time that life existed on Earth, it didn't rely on oxygen. And so other planets with life less oxygen-loving than that on modern Earth could also happily have phosphine as a popular biosignature. So I imagined a distant planet, not unlike the early Earth, a wet, anoxic, tropical paradise from pole to pole, with a rich anaerobic biosphere that could produce tremendous amounts of phosphine into its atmosphere. And I worked really hard to figure out what kind of telescopes we would need to spot such a biosphere, hopefully somewhere within my lifetime. And some of you may not know that phosphine turned out to be a little more exciting than I had initially envisaged. Because a few months after I submitted this work, an astronomer at Cardiff called Jane Greaves reached out to me asking for help with interpreting a telescope signal seen here in white, and later a follow-up observation shown here in orange that seemed to indicate that phosphine might be present in the clouds of Venus, the only potentially habitable location on the planet. Now, Jane knew this was strange, but needed a phosphine expert to know how strange, and that's how our collaboration began. First, we tried to estimate how much phosphine could produce this signal, and it seemed to correspond to a phosphine concentration of parts per billion, which is much higher than the parts per trillion or parts per quadrillion that we find on Earth. And then we tried to figure out if, in the extreme environments that you can find on Venus, maybe phosphine had false positives for life. But we couldn't, no matter how hard we try, explain such amounts of phosphine on the clouds of Venus with any conventional physics or chemistry. So the notion that phosphine, a molecule I claim to be a promising biosignature, might be present on Venus is of course very exciting, and the press thought so too. But before we jump on life as an explanation, I should point out there's still much about Venus we don't understand. So all we really know is that something strange is happening on Venus. And currently, there is plenty of controversy surrounding this potential discovery. But ultimately, we need to address the primary uncertainties of this discovery. Namely, is the signal definitely real? Because it could be noise. These are very difficult observations. 2, if it is real, is it unambiguously phosphine, or could it be another molecule pretending to be phosphine? And finally, 3, if it is real and it is phosphine, what is making it? To try to answer these questions, I will be looking at Venus again when it becomes available in the sky in July. And as we learn more about Venus, perhaps we can get more, better models that can help us make sense of exactly what's going on in the clouds of Venus. But to make the most of both models and observations, we need better spectroscopic data that can not just describe phosphine, but every other atmospheric component of Venus and how they interact with one another. This spectroscopic toolkit will be vital for us to understand what's happening on Venus, and I am working on it. But what I want to highlight at this point is how a virtually unknown and quite unusual and disgusting molecule became such an important piece of the puzzle in the search for life beyond Earth. And phosphine is just one molecule, Venus just one planet. Even if it turns out that indeed we have found phosphine on Venus, this will not be the last time we find a potential biosignature on a planet beyond ours that is potentially inhabited. Phosphine may be a very special biosignature, but there are billions of stars in our galaxy alone with billions of planets orbiting them. And these planets could contain trillions of life forms, releasing thousands of molecules into their atmospheres, just waiting to be detected. And all of these wonderful possibilities are only available to us because we are beginning to understand what the spectra of molecules looks like. Phosphine can only be detected because we have begun to understand its quantum behavior. This deceptively simple-looking spectrum on the screen is formed from the collective force of 16.8 billion tiny features, each of whom represents a very particular form of quantum vibration or rotation of the phosphine molecule at very specific frequencies of light. And the complexity of these vibrations, these frequencies, is really hard to visualize and even harder to understand, which is why it is wonderful to work with David on this project, who has sonified the phosphine spectral frequencies that you see here to the audible range. So it is with great pleasure that I bring you what I think is the world premiere of The Sound of Phosphine.
Absolutely, it is. Thank you so much. Let's have a round of applause for Clara, actually. This is a good time. Sharing her wonderful work for the third time, I should say, with Multiverse. Not the last, I hope. So here is, I'm about to introduce a world premiere. I've been fascinated by phosphine ever since learning about it from Clara. So she showed you the spectrum, and you might have noticed, the very keen-eyed amongst you have noticed one large peak, which comes out as a cluster. And then three distinct lines in the higher frequencies. To explore that, I'm going to announce the world premiere. It's a piece for cello, performed by guest cellist Minjin Chung. And Minjin has been working with Multiverse for several events now. And the incredible thing is we've only met for about 15 minutes where we talked about doing the project heavily masked and sort of handing over some microphones and things. This has been a remote collaboration, but we already feel like friends and collaborators, and we've worked so hard to create the interpretation of this piece, and Minjin has put her heart and soul into preparing it for you. While writing Phosphine, Life Anaerobic, I imagined a new tree of life, with microbes thriving in deep oceans and clouds of other worlds. Phosphine is poisonous to us, but not to them. We live parallel lives, perhaps with parallel struggles, experiences, art, and parallel music.
Phosphine may be a very special biosignature, but there are billions of stars in our galaxy alone, with billions of planets orbiting them. And these planets could contain trillions of life forms, releasing thousands of molecules into their atmospheres, just waiting to be detected. This deceptively simple-looking spectrum on the screen is formed from the collective force of 16.8 billion tiny features, each of whom represents a very particular form of quantum vibration or rotation of the phosphine molecule at very specific frequencies of light.
Let's have a huge round of applause for Minjin Chung. She can hear you, I promise. I should say that that piece is dedicated to Clara Souza Silva and her search for life. May it be fruitful. It gives me great pleasure now to introduce a guest musician and scientist who was a big part inspiring me to do this kind of work. This is Matt Russo of System Sounds. He is a physics lecturer at the University of Toronto and co-founder of System Sounds, a SciArt outreach project that converts the rhythms and harmony of the cosmos into music and sound. Their work has been featured in the New York Times and in Calm, and they frequently collaborate with NASA. He has created the sound-based planetarium show, Our Musical Universe, that takes the audience on an audio tour of the cosmos from the night sky all the way out to the edge of the observable universe, featuring music and sounds created with a variety of astronomical systems and accessible to the visually impaired. I will now pass you over to Matt Russo.
Great. Thank you very much, David. Really enjoying the talks and presentations today. So I will be talking about musical solar systems. Okay, so this is Music of the Spheres, 21st century style. So we're going to start pretty close to home, relatively close to home, with Neptune and Pluto. So you may notice that there's 2 points in their orbits where it looks like their orbits are crossing. And so you might wonder, over billions of years, with them orbiting at different speeds, how come they've never been at the same place at the same time? What is happening? And it turns out there's an interesting pattern going on here. So for every 2 orbits of Pluto, Neptune orbits 3 times. And so that means they're in a fixed repeating dance where every time they pass each other, they're nowhere near those danger zones. And so this is a stable pattern. It's not a coincidence. This is due to physics and gravity, and it's called an orbital resonance. So basically, once they get into this configuration, they're giving each other the right gravitational tugs at the right moments to keep this pattern going and going forever, or for very, very long periods of time. So we can listen to this in a few different ways. Let's start by just playing a drum for every orbit of each, I was going to say planet, but yeah, don't want to start a fight, every object, planet or dwarf planet. So you're going to hear, for every 2 Plutos, you'll hear 3 Neptunes. And then we're going to speed it up and listen to what happens. Okay, so when we sped up those rhythms by enough times, they turned into pitches. So what we just learned is that rhythm and pitch are really the same thing happening at different speeds. Once a rhythm happens faster than about 20 times per second, your brain starts hearing it as a musical pitch. And so each of these objects has a different orbital period, and so they produce different pitches. And you may notice that those pitches sounded pretty decent together, right? It was this. And we call that a perfect fifth. So it's the first 2 notes of Twinkle, Twinkle, Little Star. Right? So that's kind of interesting that those 2 planets made 2 notes that sounded pretty harmonious. And there's a secret behind that. So imagine on the left here, you've got a giant cello string. And like we just saw, when someone bows it, it's going to vibrate back and forth at a certain rate, a certain frequency, and make a certain note. And if we cut the string in half, we'll get 2 strings that vibrate twice as fast, and that'll produce a related note, an octave, or 3 times. So the secret behind musical harmony is that different notes are vibrating at simple ratio. So 2 to 1, 3 to 2. Those are the ones our ears sense as being more harmonious. And this was first discovered over 2,000 years ago by Pythagoras. So he was especially fascinated with the perfect fifth interval we heard between Neptune and Pluto due to a 3-to-2 resonance. So fascinated that he devised an entire tuning system built just from stacking these perfect fifths on top of each other. And that was the system used for over 1,000 years before we adjusted things slightly. So that brings me to the TRAPPIST-1 system. So if you were in Dr. Albrow's talk this morning, you would have heard about this. This is an amazing system of 7 Earth-sized planets that are orbiting a nearby red dwarf star. This was announced in February of 2017. So they're all about Earth size, and about 3 of them are in the Goldilocks zone. And we think that some of them at least could support liquid water. So it's a very exciting system, and it happens to be pretty close by, so we can learn a lot about it. And one thing you have to know is that this is a miniature solar system. So if these are the orbits of the inner terrestrial planets in our system, all 7 TRAPPIST-1 planets are tucked in that little blue spot there. So I have to expand it by 25 times just to see their orbits. And so this solar system is much more similar in scale to Jupiter and its moons. The star TRAPPIST-1 is actually about the size of Jupiter, and the orbits of the planets are close to the orbits of Jupiter's moons. But they're Earth mass, so that's a lot of mass in a small space. So this is the most musical solar system ever found. So why is that? Well, TRAPPIST-1 is a resonant chain. So for every 2 orbits of the outermost planet, the next one orbits 3 times, and the next one 4, and then 6, 9, 15, and 24. So all 7 planets are locked together in an orbital resonance, which means they're all playing together, playing the same song in harmony. So what we can do is we can listen to that in 2 ways. So we can listen to that as rhythms, or we can speed it up, and that would produce musical harmony if we speed it up to the right amount to be in our human hearing range. And it actually produces this really gorgeous, sweet chord. And so what I'm going to do is I'm going to play the rhythms of this system and the harmonies of the system at the same time. So I'm just going to play a note for every orbit of each planet. And the note I play is determined by the note you'd get if you sped up their motion tens of thousands of times to be in the human hearing range. So let's see what we... Okay, so I just love that harmony. And it turns out that it goes a little deeper. It's not just this cool curiosity or this interesting thing, this interesting correspondence between music and astronomy. It goes deeper. So when the astronomers first discovered this system, they simulated the orbits based on what they knew about the planetary orbital parameters. But they found that when they run their simulations, most of the time, after a couple 100,000 years, something like this would happen. They'd be running and running and running, and then boom. These planets are so close together that they're disrupting each other's orbits, destroying the system. And so clearly this didn't happen because the system is still there. So something must be keeping this system stable. And my collaborator was the one who figured out part of the solution to this mystery. He found that you have to simulate their orbits from when they first form while the planets are inside a disk of dust and gas. Because while they're inside the disk, that's where they're allowed to move around and slide, and they can adjust everything about their orbits. So their orbital periods, but also the slight tilt of their orbit, how elliptical or oval shaped their orbits are. So it's kind of like with an orchestra, if you go see an orchestra, they don't just all jump on stage and start playing. Right? They have to sit in the right spot. They need a conductor to make sure they're synchronized. And importantly, they have to tune their instruments so that they resonate with their neighbors. And so something very similar happened to TRAPPIST-1 in its early formation. Planets could tune while they were in the disk. And then when the disk disappeared, they were able to keep their tuning. And my collaborator, Dan Tamayo, found out that when you do it like this, they become stable for billions and billions of years. So everything has to be just right so that every planet's in the right place at the right time to keep this system alive. So it's music that's keeping this solar system alive, is the way I like to think of it. But it's not the only one. So about a year later, in 2018, they announced the discovery of K2-138. This is a near-resonant chain of 5 sub-Neptune planets. So near resonant just means they're not quite in tune anymore. They probably were early on, but they've drifted a little due to tidal forces and other things that shift their orbits a bit. But early on, they would have had this amazing tuning. So there's 5 planets here, and the gap between each one is a perfect fifth. So they're all locked in 3-2 resonances. So this is Pythagoras' favorite interval. So I'll rate this solar system as 4 Pythagori out of an unlimited amount. And so that sounds like this. Really peaceful, kind of dreamy sound. And when they first discovered it, they had hints of a 6th planet. That's that far one out there. But they didn't know its orbit. So for a while, about a year, I was waiting to see, like, is it another perfect fifth? Is it something else that sounds good? Something that sounds terrible? And then in 2019, they announced they found the orbital period of that 6th planet, and it's tucked way down here. So it's super low. It's not traditionally considered a harmonious note, but it does add something interesting to the Pythagorean dream. So let's play the dream, and then I'll add that 6th note, 6th planet. So it's a bit of a strange dream. And then now we're at 2019, they discovered K2-187. And this has 4 planets in orbital resonances, but look at the resonances here. It's 15-8, 5-2, and 15-4. So those are not as simple as the ones we're used to, 3-2 or 4-3. So that means these notes are not going to sound as harmonious. They happen to just be more tension-filled harmonies. And it turns out that when you convert this into musical pitches, you get the same harmony that was used as the theme music for Alfred Hitchcock's Vertigo. So I can't really do this justice on a guitar, so I'm gonna play a version that uses the instruments used in the Vertigo theme song. That brings us to the beginning of 2020, when they announced the discovery of HD 158259. And I'll call this the super Pythagorean dream because this has 6 planets. And in this case, all 6 of them are tuned to a perfect fifth interval, or a 3-2 ratio. So we finally completed the dream. So this gets a rating of 5 Pythagorae. So here's what that sounds like. I'll play a bit and then I'll improvise a little bit on it. Okay, nice and sweet and pleasant. And then finally, this brings us up to just a little over a month ago, they announced the discovery of TOI 178. So there's 6 planets here, and the outer 5 are locked in resonance. So kind of a mishmash of intervals here. We have a 4 to 3 interval, which is a perfect fourth, some 3 to 2s, and then an octave, which is 2 to 1. So as a rating, this would get 1 upside down Pythagoras, because a 4 to 3 is actually the inverse of a 3 to 2. A perfect fourth is an inverse of a perfect fifth. 2 3 to 2s, and then an octave, which is a combination of a Pythagorean interval and an inverted Pythagorean interval. Okay, so to finish, I'm going to play the harmony of this system and then have a bit more fun with this. Thank you very much. That's it for me.
I want to have a round of applause for Matt Russo and System Sounds.
Thank you.
And there's lots of his work. He has a wonderful TED Talk. You can Google and System Sounds. A lot of these videos are up online to inspire you all. So we've got a final piece from me, and it's called Equals Life. And it's back to these sonifications, chords again. In fact, it's a 4-chord song. You might have heard one of those. But in this case, the 4 chords are 4 sonifications. The water vapor that you've heard. Oxygen, which just has a single defined dip. Methane. And the red edge from before. The reason these 4 signatures are important is because they are all clues that indicate the presence of life as we know it. Water vapor we think is essential for life. Of course, it may not be. It certainly is here on Earth. Oxygen is a factor of life here on Earth, and we have reason to think that it could be on other worlds. Methane and oxygen together are a volatile mix of gases, which you're likely to find only if they're being continuously produced by living things. And of course, the red edge of vegetation. So this is another video featuring Beth Sterling, myself, and Amelia C., and with animations produced by the Charles Hayden Planetarium of the Boston Museum of Science.
try to trace the colors of your world and mine, but I'll take my time, 'cause maybe this sum equals life.
That is our show. Huge thanks to everyone involved. In fact, if you're still here, I know some of us had to go, let's have everyone in the gallery view, and we'll have a round of applause for all of our Multiverse concert performers. I'd like to thank, in turn, Beth Sterling, soprano, Amelia C, violin, Minjin Chung, cello, scientist Clara Souza Silva, and Matt Russo of System Sounds. A special thanks to our album artist, Marlena Bokian-Hewitt. You can see some of her art in the gallery, and of course the album cover I'm wearing, and the Kickstarter backers that made Octave of Light album possible. If you've enjoyed the show and the festival and want to support us making these events possible, your donations will go towards all three of the organizations, Multiverse, SciArt Initiative, and CLOT Magazine. And everybody who donates will get the album Octave of Light as download on Bandcamp. If you haven't already or would like to support us more, visit multiverseseries.org and click support. And your funds will go towards covering our costs and helping us to do more events like this in the future and continue to connect art and science and shared humanity in the best way that we can.